We are Group 16 and we are studying Battle of Midway. Let's take a look at bottom line up front for the Battle of Midway. The battle took place in the Midway Atoll, and the Imperial Japanese Navy and the United States Navy were the two sides of this battle. And the outcome of this battle was a United States victory, that the Imperial Japanese Navy ended up losing all 4 of its aircraft carriers. This battle was particularly important for the World War II because Japan was planning to use Midway as a launching point for further attacks to expand their presence in the Pacific and finally to attack US mainland. With the US victory, the rise of the US Navy started in the Pacific scene, and Imperial Japanese Navy, the Empire of Japan, started declining in the Pacific after this battle. So this was a turning point. A key debate regarding the Battle of Midway is known as Nagumo's dilemma in the literature. Admiral Nagumo of the Imperial Japanese Navy sent his bombers to attack the island of Midway to cripple the island. What he didn't know was the US aircraft carriers. And midway in the first wave attack, one of the Japanese scout planes detected the aircraft carriers of the US Navy. And now Nagumo was met with a dilemma. He either implements the Navy's doctrine, the Imperial Japanese Navy's doctrine, of attacking with full force, so he waits for all of his bombers to come back, rearms and attacks the US Navy aircraft carriers, or he doesn't wait and he immediately attacks with the small contingency of 20 torpedo planes he has on board. And this is what we will study. Expanding on Nagumo's dilemma, our research question is, how would the casualties change for the Battle of Midway if Nagumo decided to attack the US Navy aircraft carriers after receiving the message from Tone 4 scout plane that detected the US Navy aircraft carriers? By proactively countering the attack with bomber planes on board, instead of waiting for the aircraft attacking the US forces on Midway Island to return. Here our hypothesis is by acting quickly to attack the US Navy aircraft carriers instead of waiting for their bombers to return, the Japanese Navy would have inflicted more damage on the US forces and reduced their casualties. To answer our research question, our dependent variable will be the casualties were Japanese and US Navy. So actually we have 2 dependent variables that we will investigate, and you will see some of our results of the statistical analysis today. In addition, for our independent variables, as previously stated, we will use the number of Japanese bomber planes fitted to attack the US Navy carriers and the number of fighter planes to assist these to protect these torpedo planes during their attack. In addition, given the comments we received and also reconsidering our research question, we added the Imperial Japanese Navy's response time. In other words, the time it takes for Nagumo to launch the first wave of attack against the US carriers is yet another continuous independent variable that we will study in our simulations and our statistical analysis.
One of Japan's main goals during World War II was to remove the United States as the Pacific Power so they can gain the territory in East Asia and South Pacific Islands. Japan wanted to defeat US and they wanted to use Midway as the base to attack Pearl Harbor. The main reason was to secure the dominance in the region. The leaders for the Battle of Midway from the Japanese side, Admiral Yamamoto, Nagumo, and Kondo. From the American side, Admiral Nimitz, Fletcher, and Spruance. The relevant history and technology. The place of the battle was North Pacific Ocean. Environment was, of course, ocean. The timeline of the battle, though it extends, but we are focusing on June 3rd to June 6th of 1942. And the outcome of the battle was an overwhelming success for the Americans, crippling the Japan's ability to control the Pacific. On the technology side, the Americans had 3 fleet carriers, 7 heavy cruisers, 1 light cruiser, 15 destroyers, 233 carrier-based aircraft, 127 land-based aircraft, and 16 submarines. On the Japanese side, 4 fleet carriers, 2 battleships, 6 heavy cruisers, 1 light cruiser, 14 destroyers, and 248 carrier-based aircraft.
Here, we are going to talk about agents. We have 4 types of agents in the model: ships, fighter planes, dive bomber, or torpedo bombers. We have total 488 agents in the model. Each dot represents carrier, fighters, carrier attackers. The model has total 7 fleet carriers, 481 carriers-based aircraft. Each agent will have same parameters for quicker development. Of course, not all the agents' parameter will truly matter in the NetLogo model, but creating a generic agent that will encompass all type of agents will allow for more accessible interactions to be made. Health will be a variable we research in depth, as we try to determine how many rounds from an aircraft gun can take out different planes, how many bombs, torpedoes it might take to take out an enemy ship, and how many machine gun bullets it might take to take out a plane. Health for bombers will start at 50, fighters at 30, carriers at 100, but will decrement differently based on what type of agent they are and what type of ammo they were hit with.
We did not have a change in our resources for the conceptual model, and here this is given for your reference. The only takeaway here is we extracted the average speed, cruise speed for different agents, for different turtles, and also the minimum and maximum so that we can create more realistic dynamics in our model. And here are the resources for the Japanese turtles that we have in our model. Again, the idea is the same. Our resources are the same, and we extracted the average speed and minimum and maximum for realistic dynamics.
The conceptual model environment. With regards to the distance each patch represents, we will have 1 square mile equal to 1 patch. With regards to patches having any other parameters, well, as the battle took place mainly in the open ocean, there won't be any concerns for implementing ground cover elevations or different speeds of turtle based on the terrain. With regards to where we have found this data for these parameters, there is no reason to model the environment as it takes place in an open ocean. And in this case, we have used the general bathymetric chart of the oceans, global terrain model, for ocean to validate the distances.
Yeah, so moving on to our agent behaviors here, I won't go too much in depth on these next 3 flowcharts as our model does take about 3 minutes to run, and you'll actually see a lot of these behaviors in the actual run of that model. But the 2 things to take away from this fighter plane flowchart are I guess the 2 bottom diamonds, where if there's an enemy bomber in sight, the fighter, we want that fighter to engage that bomber to try to protect its carriers. And that bottom diamond there, if there's an enemy fighter in sight, we want the friendly fighter to try to take that fighter out so it can kind of clear the lane for its own bomber to get to the aircraft carrier to drop its payload. Moving on to the dive bomber and torpedo bomber flowchart on the left side there. The gist of it is really checking to see if it's been shot down, seeing if it's found a target. If it hasn't, look for a target, and if it has found a target, in this case, a carrier, whether that be a red side or blue side, it will actually attack that carrier with its munitions. For the ship flowchart, pretty simple on this one. It really just looks up at the sky to determine if there are enemy bombers or fighters coming down at it to attack it. And if there are enemy bombers or fighters, it will actually engage those enemy bombers and fighters with its anti-aircraft munitions as well. It also does a check in there to see if it has any health left to determine if it's alive or not. Yeah, so here we have the entire view of our model. We have the buttons up there on the top left, set up, reset, and go. And then we have a bunch of sliders that we can control the different number of blue fighters, red fighters, and red bombers. Finally, we have a couple beautiful plots here with active bombers and active fighters for both the blue side and the red side, as you can see by the lines there. We actually zoom in on this blue part, kind of in the middle, so that viewers can see the agents actually interacting with each other, which you will see in the demo. Yeah, so we've added a few sliders to our model since you've last saw it to really vary the number of blue fighters, red bombers, and the Japanese attack time in our model. The number of red bombers and the opportune Japanese attack time are two big variables in determining what the Japanese could have done better during the Battle of Midway. So those are two variables that we're looking at changing along the way. We also have plots here for active bomber counts for both red and blue sides, and then active fighter counts here down below. Moving on to the actual run of our model, we see we have the US side down here in the bottom right, already with some planes up in the air, and then the Japanese side in the top left up here. So we'll go ahead and run it. You can see the purple planes here are the fighters going out ahead to determine if there are any enemy fighters in the area, giving the blue bombers a path through to get to those ready carriers to drop their payload. So you see there, the blue bombers drop their payload, no aircraft carriers on that run, and here comes the humongous wave of red bombers. So as you saw, I put the red bombers number at 100. That is completely obnoxious. That number is normally around 25. But for this case, to really showcase the independent variable that we will be varying, I was a little dramatic with it. So you could see the orange fighters here from the Japanese side running out ahead, trying to determine if there are any blue side fighters, which are colored purple down here in the bottom right. Those blue side fighters, I should say, will be trying to protect their carriers from the incoming barrage of red bombers. So we'll go ahead and play it, and then you'll see these purple fighters shooting at the incoming wave of red bombers, trying to take them out before they get to their carriers. And then the actual orange fighters, or I should say the red fighters, we colored them orange in this scenario so you can tell the difference, but the Japanese fighters will be trying to take out those blue side fighters as well to protect their red bombers. So go ahead and play here. Again, a ton of red bombers, totally unrealistic, but you can see in this case, all aircraft carriers were destroyed on that first run, on that first wave. So our model is usually about 4 to 5 minutes long. Unfortunately, we won't be able to show the whole thing during this time duration, but it really is just a continuation of wave after wave of attacks from the Japanese side and the US side until one of them eventually comes out victorious. So that's our model. That's some of how the agents interact with each other, and more importantly, probably the information about the independent variable of the number of red bombers and the Japanese attack time that we'll be researching.
Let's take a look at our statistical analysis. As you may remember, our research question, in a nutshell, is the impact of Imperial Japanese Navy attacking the US Navy carriers quickly right after they know that the US carriers were around, as opposed to waiting to scramble even more fighters and bombers and delay their attack. Here our independent variables are the numbers of Imperial Japanese Navy's bombers and fighters, and also the time tick in the simulation at which Imperial Japanese Navy starts their first wave of attack against the US Navy carriers. You can see the baseline values for all these independent variables for which we've obtained parity with what ended up happening in the Battle of Midway. And you can see our experiment values that cover these baselines, but also explore values that are above and below. And here our dependent variables are the casualties for the Imperial Japanese Navy and United States of America Navy. And these casualties include planes and carriers. Our statistical analysis steps are designing these experiments. We did random sampling, and you can see the experiment ranges here. We've designed 1,000 simulations. And after we run the simulation for all these 1,000 parameter combinations, we have performed correlation analysis to assess how related are these independent variables pairwise with these dependent variables. Next, we form a linear regression model for the Imperial Japanese Navy's casualties and USA casualties separately to assess the impact of these independent variables. Lastly, we perform a sensitivity analysis to take an ANOVA approach to see how the variability in these independent variables correspond to the variability in the dependent variables. Now let's take a look at the correlation coefficient analysis results, one thing you can see here is the correlation coefficient on the left for all 1,000 simulations. And also we divided our results up into subsets where the simulations ended with a Japanese victory, which is what you see on the top right, and simulations where it ended with a US Navy victory that you can see at the bottom right. One thing we see for the total numbers is we don't see a strong linear relationship between our independent variables and the casualties. However, when we look at the case where Japan wins, we see a very strong relationship with the number of bombers they use and the casualties they inflict on the United States. In addition, we see high Japanese casualties for high number of bombers, but this is somewhat of a trivial relationship. Lastly, what we observe are if Japan's attack time is varied, the US casualties also vary. In other words, Japan's attack time is quite important in the amount of casualties that they can inflict. Whereas for the US Navy, cases where the US Navy prevails, we don't see a very interesting relationship, at least strong correlation. The only strong correlation that is more than 0.5 you observe is IJN casualties being strongly related to the number of IJN bombers. This is expected as these two variables are very closely related by design. We performed 6 separate regression models. We fit 3 different regression models per IJN and USA casualty variables separately. On the left are the regression models where the dependent variable is IJN casualty, and on the right, the dependent variable is the USA casualty. For every dependent variable, we define 3 regression models. One for all of the simulations, another one for simulations where Imperial Japanese Navy wins or prevails, and another one where USA Navy prevails. Let's investigate these regression models for Japanese casualties. We observe all low R-squares and the coefficient of determination, which indicates that the strength of linear relationship is not strong. The strongest one here is the case where USA prevails. We see that the most important variable is the number of IJN bombers, and as we discussed, this is somewhat trivial. However, when we look at USA casualties, we see that the case where Imperial Japanese Navy wins, we see that the number of IJN bombers, so the raw number, in addition, the time of the first Imperial Japanese Navy attack are significantly higher, which means that in addition to the raw number, the time of attack does make a difference too. And the R-square here is 0.54, which indicates that there is a somewhat strong linear relationship. However, looking at all these simulations, one thing that we observe are relationships are not linear. This is a complex system, so we might need a different approach to understand relationships. And for this reason, next we go to Sobel sensitivity that doesn't assume linear relationship. So for those of you who are not familiar, Sobel sensitivity relates the variability in the independent variable to the variability in the target variable, the dependent variable. So here we are modeling the variability that we observe in the casualties as a combination of the variability of different independent variables. When we look at first order, that means that the direct impact of a variable, we see that the number of the raw numbers make the most impact on IJN casualties, which again is trivial. And we observe here that the time of attack doesn't really make a big difference for IJN casualties. But we discussed that IJN casualties is somewhat trivial. When we look at casualties of USA that are inflicted by Imperial Japanese Navy, we see more interesting patterns. One thing we see is even though the number of bombers and fighters for Imperial Japanese Navy do change the USA casualties quite a bit, the initial attack time, the first order impact of initial attack time is quite important. And when we look at the second order sensitivities, we see a very interesting interaction, and I will highlight it over here. We see that the number of IJN fighters and the initial attack time do have a very strong second order relationship. In other words, the interaction between these parameters is important. And here what we can see is if Japan launches an early attack and if they have a lot of fighters to protect their bombers, they can inflict a lot of casualty on US, which is an interesting finding that supports our initial hypothesis.
Lastly, we tried a random forest regression and classification model to model the driving factors behind casualties. Our attempts at creating a high accuracy classifier that can predict the Japanese and American casualties did not yield a predictive model. The highest R-squared we could obtain was 0.02, whether we tried to predict American casualties or the Japanese casualties. This is partly due to having only 1,000 samples and partly due to casualty numbers showing great variation in our experiments. Next, we tried a random forest classifier to explore impactful factors behind who ends up winning the battle. In other words, we use the victor variable as our target variable. In this case, we have an R-score of 85%, which is the highest accuracy model we've ever created. The variable importance here sheds light into the driving factors. We see that the number of IJN bombers is the most impactful variable. Secondly, the attack time is also most impactful, thus giving us a similar answer compared to Sobo's sensitivity, with the added benefit of modeling these variable importances in the context of prediction as opposed to sensitivity. In conclusion, our initial analysis is supported by our results. We see that Nagumo attacking earlier makes a difference in the damage IJN can inflict on the USA. Also, our random forest shows that the number of bombers and the timing of the attack combined can really change who wins the battle. So Nagumo did have a fighting chance if he acted earlier. Our sensitivity analysis shows an early attack could have given the IJN the edge if they were able to convert all bombers to torpedo planes quickly. And our random forest model indicates that predicting the victor shows the time of attack and the number of IJN bombers could have changed the outcome of the battle.